you very much. I'm very happy to be here again. Coggin called me and said, would you come and visit with us another time? I said, didn't I do it right the first time? You're very kind to include me in these special celebrations, and I want to have each one of you meet Oliver. Oliver is our family dog. My wife is a volunteer with the American Red Cross, and she is in Carolina helping with water issues. And Oliver is 4 years old. We're going to talk about numbers for just a few short moments. I was here 11 years ago. A friend of mine, his name is Henry, his mother just told me that she met me 40 years ago in Madison. Today marks the 61st anniversary of my leaving my native Lebanon with my father, mother, and two younger sisters coming to America. Numbers are significant. Anniversaries are significant because they give us time to reflect. So, Henry, are you ready to take Oliver from me for the duration of this program? All right, here we go. And Henry said, your mother was as old as you are now when we met, so don't tell us how old you are. Numbers, small numbers, big numbers, numbers for measuring temperature, numbers for measuring time. 14 billion years ago is when the Big Bang happened, and that's when hydrogen was formed. A few million years later, oxygen was formed. And 4.6 billion years ago, our planet was formed. And everything that we have on the planet was formed there, including water. The water that we drink now is 4.6 billion years ago. The water falling down on Carolina and the East Coast is that old. Its composition hasn't changed, but our understanding of water has become a lot better than what our ancestors knew. Water is a unique substance. It's the only substance on Earth that exists in three stable forms, and it's constantly moving among them. You know what they are. Solid water is ice, liquid water, and then water vapor. Water is essential to life as we know it. Water is essential to the quality of life around the planet. Water is a precious resource, a precious natural resource. Right now, around the planet, there are 1.3 billion people who cannot do what I'm about to do now. Take a sip of clean water. We live in the most advanced scientific and technological society in history, and yet more than 1/5 of the inhabitants of the planet are deprived of drinking clean water. How can we, as responsible, learned individuals and groups, tolerate that? How can we tolerate having people not only overseas but in our country be deprived of this precious resource that is essential for life as we know it? And water has a lot of interesting properties. Not only does it exist in three phases, stable phases, but it has many interesting properties. For example, and everyone knows this, If you take an ice cube and you put it in a glass of water, where would you find the ice cube when you look at the glass of water? At the top of the liquid or the bottom of the liquid? At the top, because ice is less dense than water. Ice floats in water. That's saying the same thing in different words. And in science, we try to satisfy our curiosity by asking questions, such as, how come ice is less dense than water? We ask all kinds of questions. Why is the sky blue? Why do the leaves change color in the fall? Beautiful color transformations that we are beginning to enjoy now. And are these transformations affected by water? Or by water vapor? Or by temperature changes? Or by the amount of sunlight? Yes, they're affected by all that. And why is it that the giant factories that make chlorophyll by a process we call photosynthesis, why is it that this process of making chlorophyll shuts down, begins to shut down? It begins to shut down because there's a change in the amount of water vapor in the atmosphere, a change in the humidity, a change in the amount of sunlight, a change in the temperature. And you know from your own personal observations that the duration of the season for color changes varies from year to year because of these factors, primarily because of these factors. We're all curious about what happens in our beautiful, complex world. Because everything around us is made of chemicals. The air that we breathe is usually a mixture of chemicals, usually good chemicals. Our clothes are made of chemicals. Our own bodies are made of chemicals. The medicine that we take when we are sick is a mixture of chemicals. The drugs that some people very stupidly experiment with are chemicals. And that's why we need to learn about chemicals, their proper handling, their safe handling, their benefits, a proper disposal of them, so we can all enjoy the beautiful, complex world that we live in. And water is an essential chemical to life as we know it. So, we want to try to increase our appreciation as well as our knowledge of water. So, how old is the water that's in my bottle right here? It's pretty old, I know, pretty old, but how old is old? It's 4.6 billion years. You know, that's an interesting number. How do scientists figure things out? Of course, we ask questions. One of the most difficult questions we do, one of the most difficult things that we do in science is to learn how to ask the question so we have a fighting chance of getting a reasonable answer to it. So how do we know the Earth is 4.6 billion years? How do we know that the Big Bang was almost 14 billion years ago? It was actually 13.6 billion years ago. How do we know that? What is the basis of knowledge? All of these questions are great adventures of a human mind. And the human mind has great capacity to conquer all kinds of challenging questions, including how do we get along with each other better? How do we respect each other? How do we treat each other with respect? In many of our conversations nowadays, the element of respect is missing from the conversation. When I speak of respect, I mean respect for the other person as a fellow human being, not necessarily respect for the ideas and beliefs that they have, but respect is crucial to our success as a society. So I wanted to share these thoughts with you as we embark on a series of experiments that relate to water. Water is said to be a universal solvent. Lots of things dissolve in water. Lots of other things do not dissolve in water. Does concrete dissolve in water? Does the floating ship dissolve in water? But it floats in water. If I take a nail and I drop it in water, it sinks. But the huge ship floats in water. How do we think about these questions and try to make sense out of them? Try to make sense that we can share with each other. So water is an important chemical, and we have to be protective of it. When we do science experiments, we always obey the safety rules, so I want everyone to see that I'm going to put my goggles on because I am a person who obeys the safety rules. And the state law says that I should wear eye protection, and I'm a law-abiding citizen, so I'm going to obey the law. And I do it for that reason, but I also do it for another profound reason, namely, it's for my protection and your protection. So we always should think about what it is that we're doing, what we're acting, so that we be responsible. And the state law says that we should also have a fire extinguisher ready to be used just in case something goes out of control. I'm not planning on anything going out of control, but we have it as a safety precaution. And I'd like to show you how this works. So if you're ready for this, I want to alert everyone in the audience that there will be some loud sound here. Oliver, you ready for this loud sound? You know, dogs don't like loud sounds. You know that, right? So I take the fire extinguisher and I press. And what did you see coming out of the nozzle here? Did you see carbon dioxide? No. This is a carbon dioxide fire extinguisher. Carbon dioxide is an invisible, colorless, odorless gas. But when I push down, I'm going to do it one more time, Oliver. You're okay, Ollie? All right? He's not shivering, is he, Henry? He's all right? I know about dogs, and I know about fireworks. And the effect of, all right, so here we go. I push this. And what you see is a mist. What you see is the condensation of water vapor that is in the environment on the cold carbon dioxide gas that's coming out of the nozzle here. And when the temperature of the mist, of the cloud, of the tiny amount of fog that was formed, when the temperature reaches the room temperature, then it dissipates and we can't see it anymore. All right? So this is not a toy. This is a safety device. I'm going to put it right here, and we all know where it is just in case I need to use it. So carbon dioxide is a gas. It is in the environment, but we, human beings, since the Industrial Revolution, have put more carbon dioxide in the atmosphere than ever. We've done that because we have relied very heavily on fossil fuels. And the Industrial Revolution has helped us all. All the advances in science and technology are the result of research and technology, all aimed to improve the human condition. But science also tells us that some of these chemicals that we put in the environment are harmful to the environment. And so I say to you that the warming of the planet is a very serious matter for us. And there are gases called greenhouse gases, and they include carbon dioxide and water vapor. And those two gases are very, very important in affecting the temperature of the planet. And that's why I want to do some experiments, first with carbon dioxide. The experiment I want to do with carbon dioxide is one where I'm going to take solid carbon dioxide. It's called, what's it called? Why do you suppose it's called dry ice? Because it's not wet, right? So that's why it's called dry ice. And the dry ice is a solid at a temperature of minus 78 degrees Celsius. Here's a chunk of dry ice. It looks like a piece of chalk, but it isn't. And it changes from being a solid to a gas directly without melting. We call that process sublimation. Can you say sublimation? Sublimation is happening right now, but we can't see it. How come we can't see it? Because carbon dioxide gas is colorless. It's invisible. And it's also odorless. But sublimation is happening right now. And the change from a solid to a gas is a process that actually is very familiar to all of us, if we think about our experiences. So, in the wintertime, you must have noticed, that the level of the snowbank goes down even though the temperature is still below freezing. That's because ice also undergoes sublimation. So sublimation is a process where the material changes from a solid to a gas without melting. And if you have a frost-free refrigerator at home or wherever you work, you know how that works? Well, the same idea, same principle. There's a stream of air being blown in there, so if any frost is formed on the inside, the stream of air gets the water vapor removed, and that's how the frost-free refrigerator works. So this is dry ice. It's undergoing sublimation. We can't see it. But we can do some experiments with dry ice, and I ask you now to look at what you see between my two hands here. You see 1, 2, 3, 4, 5, 6 glass containers. What shape are they? They're cylindrical, right? And what do they have in them? Hello? Is anybody out there? What do they have in them? Mumble, mumble, mumble. I love that sound. You know why I love this sound, mumble, mumble, mumble? Because each one of us, we live in a free country. We're free to report and say whatever we want with responsibility anytime we want to. Don't you ever forget that. And don't you let anyone else desecrate the great principles that we in America believe in and live. Well, I can ask a question, get the same answer from everyone. How many cylinders are there? 6. And what's in the cylinders?
Grape soda.
Mumble, mumble, mumble again. I love that sound. I love that sound. All right. So these cylinders have in them colored material. They could be liquids or they could be gels. How do we find out? We use our experience. We know from experience that if we shake something that has a liquid in it, we know what that does. So, am I shaking them? And so they have liquids, and they're colored liquids. Are they all the same color? No. What color do you see in this pair? How about in this pair? How about in this pair? They seem to be arranged according to the color of the liquids in the cylinders. Now, you all made that observation without my having to ask you about it. But part of my role here is to have us develop the skill of making good observations and then the skill of sharing those observations. So we try to make sense out of them. So I'm going to take chunks of dry ice using my gloves because the temperature is minus 78 degrees Celsius. If I don't use the gloves, then I'll have a frostbite. We have to stop this program. I have to go to the emergency room. I don't want to go to the emergency room. You don't want me to go to the emergency room. I know why you don't want me to go to the emergency room, because of Oliver, right? Because of Oliver. All right, so I'm going to take dry ice. I'm going to put chunks of dry ice in the cylinders. And you tell me what you see. You see any changes? What do you see? Just out loud. Just tell me what you see. There's that mumble mumble sound again. Those cylinders have in them water, and they have in them dyes, vegetable dyes, that change color when the liquid becomes more acidic. It becomes more acidic because carbon dioxide gas dissolves in the water to give us carbonic acid. Now, you remember that I had a chunk of dry ice right here. Here's another one here. And I talked about sublimation. We can't see sublimation. Can you see the sublimation here? Yeah. Can you see it in every cylinder? No, you can see it only in the cylinders where I put the dry ice, right? So we have to sharpen our ability to make observations and to share these observations. So you see the bubbles? What kind of bubbles are those? They're carbon dioxide bubbles. Where are they coming from? They're coming from the sublimation of the dry ice. And you see that the bubbles are rising. Interesting property of the bubbles. And some of the bubbles dissolve and combine with the dyes that are in there. Only in the cylinders where I put the dry ice. So let me ask you, what color change happened in this pair? The color change from what to what? Blue to this, right? All right. How about in this one? Pink to what? Hey, wait a minute. This is a clear and colored liquid. This is a clear and colored liquid. This one is clear and colorless. No one from now on is going to confuse the words clear and colorless. They don't mean the same thing. If we have to be successful in being respectful with each other, we have to sharpen our language and report accurately what we're seeing. All right, in this pair, the color changed from what to what? Yellow. All right. Now I'm going to tell you the names of those dyes that are in there. And I'm going to tell you also that all 6 cylinders to begin with had in them water and a little bit of sodium hydroxide, lye. And that dissolves in the water. That's an interesting property of water. And the name of the dye, of the indicator, is bromothiamyl blue. That's the name of it. Don't let the name confuse you. That's the name of it, right? And it changes color, as you see here, as the pH changes. So pH is a measure of how acidic a substance or a liquid is. To begin with, it was basic, so the blue color is the color in base. When we add carbon dioxide, it forms carbonic acid, it changes color. And the second one that I used is called phenolphthalein. That's the name of it. And that's where the pink changed to clear and, a little louder, clear and, yes, I want convictions about your observations and your confidence in sharing them with each other. This is how we learn from each other. All right, and then the last pair that I have was a mixture of these dyes, the mixture of these indicators. It's called universal indicator. And in all 3 cases, the pH, did the pH go up or go down? Go up. Don't guess, it's a 50-50 guess, right? Don't guess. Look, let's go back. Let's go back for a moment to this one here, all right? The color when the pH was high is what? And when the pH is low? All right, and so, therefore the pH went down. That means the liquid became more acidic. Became more acidic because carbon dioxide is in there. And carbon dioxide gas is a greenhouse gas. And we're putting out a lot of carbon dioxide into the air because we use a lot of fossil fuels. We're not using enough renewable energy. We're not using wind and solar and other parts of renewable energy. What is happening when the carbon dioxide dissolves in the ocean? Is the pH going to go up or go down? Go up. The pH is going to go down. That is what we refer to as ocean acidification. The oceans are becoming more acidic. And the shells that are in the oceans are made of calcium carbonate material. And calcium carbonate, when you add acid to it, it's going to break up. There are other adverse effects also of having more carbon dioxide go up into the atmosphere than is happening naturally. All right, so let me take these cards out of the way. I put the cards back there so you can see the color changes better, right? Don't you see the color change better this way than that way, right? So that's why I did it. So I'm now going to put these over here and come back and ask you, the stuff that you see coming up here looks like smoke, but it's not smoke. Let's have a little more. I like this. Isn't this pretty? It looks like smoke, but it's not smoke. You know what it is? It's condensed water vapor. It's the same stuff that came out of the nozzle of the fire extinguisher. The condensation is happening on the cold carbon dioxide gas that is coming out of the sublimation. You know that not all the carbon dioxide gas dissolves in the liquid. If it all dissolved, we would not see the bubbles. Am I saying things to you that are so obvious? Sometimes we help each other by saying things that might be obvious to me but not obvious to you, or maybe obvious to you but no one has called your attention to it. So carbon dioxide is not very soluble in water. That's why the bubbles keep rising, and then the condensation takes place here. We get this mist. We get, it looks like fog. It looks like a, it's the same stuff that's in, what floats up in the sky and moves from one place? What? Clouds. It's the same thing. That's condensed water vapor. So what I'm going to do now is take this dishpan, which is empty except for what? Air is in it. Air is invisible. I'm going to reach below and get out a very hot. Now you see any bubbles here? This is water. What kind of bubbles are those? Are they carbon dioxide bubbles? It's pretty hot. These gloves are not very good insulators, but they're good enough for what I'm doing. Now I lift it up. You see the bubbles? Are they air bubbles? No, they're water bubbles. There are all kinds of bubbles. There's even bubble gum. There are all kinds of bubbles. So what I'm going to do is take the hot water, boiling water, and empty this into the dishpan just like that. And what do you see coming off the top? Steam is invisible. Come on, we've been talking about this for some time. What you see is condensed water vapor. The hot water vapor hits the cold air. There's moisture in the air. It condenses, right? And we see it. When the temperature reaches the room temperature, then we don't see the mist anymore. It's a mist. So I'm going to take this to the side over here, and I'm going to get my dry ice bucket, and I'm going to dump the dry ice in there. I'm still here. Does that look like steam to you? No. What does it look like? It looks like fog. That's what it is. And you notice, I know it's very exciting, and I know you want to look at it and enjoy it. And I like to look at it and enjoy it too. This is how they make fog in the movies sometimes. They take boiling water and add dry ice to it and put a fan on it. But you notice that the fog is moving downward. So the condensation of the water vapor is happening on the cold carbon dioxide gas that's coming from the sublimation. And this tells us that carbon dioxide gas is less dense than air. The density is, I'm sorry, it's more dense than air. It's going down. Okay, you caught me, right? Right. You're paying attention. So that's what I want to say to everybody. It's very important to pay attention. And in science, we're always in science, we're always skeptical. No matter who says what to you, always think about it and see if it makes any sense to you. So when I said it's less dense, that doesn't make any sense. On the other hand, at the beginning of this experiment, the plume went up. and now it's no longer going up. Why is that? We always ask questions, and we are able to focus attention if we pay attention. You have to pay attention to what's going on. So at the beginning of the experiment, this one, the water was boiling, and the dry ice was minus 78 degrees Celsius. By the way, the boiling point of water is 100 degrees Celsius. It's very high. It's unlike any other substance that has in it properties similar to water, except for the high boiling point. So it's very, very important that we learn about water and its properties. And this is a good time for me to invite you all to visit my website, because I have a special entry on my website about water. And my website is www, they all start with www, scifun.org, scifun.org. You don't have to write it down, just say it a couple of times quietly. scifun.org, scifun.org. This is how we memorize things. But what good is it to memorize things if we don't use them? So, in a few days, I'm going to ask the webmaster to find out how many new hits we're going to get from Sturgeon Bay, right? So, scifun.org, look at water, look at the other experiments that we have that you can do at home, including some of the ones we're doing today, but not all of them. Water has other interesting properties. For example, if I hold this vessel, what shape is it? Is it a big cylinder or a small cylinder? Small, medium, yeah, right. How small is small? It's smaller than the other cylinders on my left. That's why you said small, right? But compared to something else, it might be bigger. So what we have to do is sharpen our powers of observation. And here's what I tell my students at the University of Wisconsin in Madison to do. Pretend you're the play-by-play radio announcer describing to someone who's with us what's going on. Not the TV announcer. The picture tells almost everything. Pretend you're on your cell phone and telling someone back home what's going on here. So you can say, these 6 cylinders, are they 10 liters in size? No. Are they 100 milliliters in size? No. They're somewhere in between. We put a bracket on it. So actually, these 6 cylinders are 1 liter in size, and they're not full to the top with the liquid. We make all kinds of observations. The brain receives all kinds of sensory input. We have to train our brains so we are able to sort out and successfully share with each other. So this is about half the size of that, roughly, right? It has water in it, and I'm going to ask you, especially those of you who are near the front who can see this. Do you see what I'm holding in my hand here? What do you see? You see a white card. Is it a big card or a small card? Do I have to ask all the questions all the time? Huh? Well, what about, is it about 8.5 by 11? Is it something like that? Huh? Yeah. So look, always make a connection between what you're observing and something you already know. Make good connections. That's what we're talking about. So I'm going to hold this up like so, and I'm going to ask you, you see the 2 arrows? Hang on. You see the 2 arrows? Yeah. Which direction are the arrows pointing? Are they pointing from my left to my right or from my right to my left? Are they pointing from my left to my right or my right to my left? From my left to my right, right? Are you sure? Okay. I'm going to put them like this. And now, what do you see now? They're going the other way? Huh? They're going the other way? This is an experiment you can do at home. All you need is a glass full of water, and you can make 2 arrows yourself, right? And if you don't want to make 2 arrows, you can take the glass of water and put your 2 fingers like this. But you have to learn how far from the glass vessel you have to be in order to see this interesting property of water. So we make all kinds of observations because we don't always believe what we see. Do you always believe what you see? Well, the arrows are going this way, and I put them behind the water, and if you're sitting near the front, you can see that they're going in the reverse. So this is part of what we call an illusion. And there are all kinds of illusions. What's one of the most common illusions that you know about? It's way up in the sky. It has to do with water. A rainbow. A rainbow. And a rainbow is an optical illusion. A rainbow. There are other types of illusions called visual illusions. Visit my website. Click on the right place, and you can learn more about illusions. You can learn more about how the brain functions. You can learn more about water. You can learn more about all kinds of other chemicals that are involved. All right, so let's see. What other experiment shall we do now? This one? You'd like me to do this one? All right. So let me hold this big one up here. Can you see that I have some white beads and blue beads? Can you see that in the back? You can see that? Thank you for telling me that you can see it. It's not just a nervous tick that you have that you're going like this, right? All right. So watch what I do. And when I go 1, 2, 3, and then I set it here. Well, it's not going to sit over here. I set it. Can you still see it? Where are the white beads now that are in the bottle? Are they still in the same spot they were before? No. Are they higher or lower? Higher. And the blue ones? Lower. And they're moving. Which way are they moving? Are they leaving the bottle? I'm listening to you on the cell phone. You've got to tell me more information. Make some sense. Come on. Rising. They're rising. Where are they rising? Like the bubbles? They're rising all the way up? No. We have to sharpen our ability to share with each other what we see. All right, so how about I take this blue and yellow and I do the same thing. And then I set it down here. And I take white and red and I do the same thing. And I take yellow and red and do the same thing. You know what? I'm going to pass these around. Do not open them, please. You can shake them and you can watch them as long as you want. I know that you're going to return them to me because you respect me, right? And I know that there are 1, 2, 3, 4, 5, 6 of them. So let's pass them around, and you can make observations about those. You pass this to the people behind you, and I have 3 to pass around this side here. And this is actually an experiment you can do at home. And thank you. Just pass them around. Thanks. And if you visit my website in the upper left corner of scifun.org, you click on experiments you can do at home, and you're going to find this experiment with the instructions on how to do it and how you can actually make those bottles and how you can think about the explanations for what is going on inside the bottle. I will tell you now that there are 2 liquids in the bottle. And if you're holding the bottle and you try to see that there are 2 liquids, you can't easily see that. Because those 2 liquids, these 2 liquids, one is water and the other one is rubbing alcohol. But the water has in it something else that dissolves. Table salt. A lot of table salt. And the beads have different densities. Some float in the alcohol, some float in the water. And when you mix them together, they get separated because the liquids are getting separated. And if you look carefully enough, you will see that there is a almost visible, it's mostly invisible, interface between those 2 liquids. You don't have enough time to observe that here, but do the experiment at home and you'll be able to understand and appreciate what's going on. So it's allergy season in Wisconsin, right? So I'm going to have another sip of water. Thank you very much. Now I'm going to do another experiment. This experiment has to do with the product of combustion. Actually, I don't know exactly where the experiment is, but I brought my book with me here. This book is called Chemical Demonstrations. This Bassam Shakhashiri down here is published by the University of Wisconsin Press. And with your permission, I'm going to open the book and read the instructions for the next experiment. Is that okay if I did that? This is not an ordinary book. This is a real hot book. You can see that, right? It's actually not a book at all. It's just the book covers of my volume 5 in this demonstration series. So I'm going to show you on this side first, and then I'll come to this side so you can see what's going on. All right? On the inside, there is a battery. Batteries have stored in them chemical energy. Up here, there's a wick that I soaked with lighter fluid when you were not looking. And there is a flint from a light bulb up here. And then down here, do you see anything down here? Here's a little button down there. All right, so I'll come to this side now, show you the same thing. All right, there, a battery down here, stored chemical energy in it, a wick that's soaked with lighter fluid, and the flint, and the filament, and then there's the button. All right, now, in order to have a fire, you need what we call the fire triangle. You need what? 3 things. You need something that burns, that's fuel. You need oxygen, usually from the air, and then you need a source of ignition. In this case, it is heat. So that's the fire triangle. How does this relate to this? Here's how you do this experiment. You hold the book, you move it away from your face. Why is that? Safety is paramount. I open the book, and when I push the button, the chemical energy changes into electrical energy, and the filament lights up. But this filament is like all other filaments except for those in LEDs. It gives off light energy and also heat energy, and it causes the lighter fluid to burn. Here we go, okay? There it is, okay? Now, you tell me out loud what happens when I close the book. What happened when I close the book? I'm hearing the mumble again. And I like that. I told you, I really like that. And all of us have to be respectful of each other to report what we want to say, as long as we are responsible for what we say. Some of you are like the students in my class. In my first year chemistry class, you give a correct answer, but not to the question that I asked. That's why you lose points on exams, right? So the question that I asked was, what happened when I closed the book? What happened when I closed the book was that the fire went out. Why did the fire go out? Because there's no more oxygen. So I opened the book now. Oops. By the way, that's why we always keep the lid on. I opened the book. Is there oxygen or not? Yes. But there's no fire. How come there's no fire? No heat. I need 3 things to have a fire, right? 3 things. So what should I do? What should I do? Push the button? Oh, yeah. No way. I'm going to move it away from my face. And then I'm going to push the button. So here we go. You see that? We teach about the fire triangle, so we learn how to put out fires, not to start fires. All right, so that's one experiment. But this combustion reaction produced carbon dioxide. All combustion reactions of fossil fuels produce carbon dioxide. And the little paper that you have in your hands shows the increase in the amount of carbon dioxide in the atmosphere as measured by scientists on the top of a mountain in Hawaii. It's constantly increasing. We are going to continue to use public transportation, private transportation. We're still going to go places flying on airplanes, but we have to reduce our dependence on fossil fuels. And we have to do that in responsible ways, and all of us should think about that so that we are responsible citizens protecting the planet that we are enjoying. So carbon dioxide is a greenhouse gas. I'm going to make a general statement to tell you that greenhouse gases are good for us. If it weren't for the greenhouse gases, the temperature of the surface of the planet would be as cold as it is on Mars, and life as we know it would not exist. But too much of a greenhouse gas is not good. That is the problem. And water vapor is a greenhouse gas, but we can't do anything about that because of the water cycle. Except that when we produce more carbon dioxide, then the global temperature goes up. That's global warming. And when the temperature goes up, then more water changes from being a liquid to a vapor. And the vapor, water vapor, is a greenhouse gas, so it is an adverse effect. So we really have to be thoughtful, purposeful, and combat climate change in ways that are helpful to the planet. All right, so now I'm going to do a different kind of experiment. This experiment is one where I have two flasks that have clear and colorless liquids in them, and I'm going to add different substances to it, to each one. They have about the same amount. I'm going to take the stopper off. Let's see, do I have any powder in this one? I'll find out. Yeah, I have powder in that one. So I added that powder. And this powder does not appear to be very soluble in water. It seems to be turbid, as we call it. It's not dissolving as much. On the other hand, the more I wait and the more I mix, let's mix it like this. You notice how I mix? I put my thumb up here. Why do I put my thumb up here? Because I don't want the rubber stopper to fly away, right? So I mix that, and then I reach for another one. Is that the same one I used? Let's find out. Let's find out. No, it's not the same one I used. So I have done the same thing now here. This is with my left hand, this is my right hand. You see, it's dissolving. So one thing that we do in science as we make observations and try to make sense out of the observations is we pay attention and we're patient. So not everything happens instantaneously. Sometimes we have to wait until we make more observations, and you can see that the solid now is dissolving in the liquid. It just took a little longer. Now I will take two different dyes and put them separately in each of those flasks. Here's the first one. What color do you see now?
Purple, purple, purple.
And then I'll take the second one. And let's see. What color do you see now?
Blue.
And for reactions to happen, we have to mix the chemicals, just like in cooking. Cooking is one of the great set of experiments in science. You know that, right? So I'm going to take this. I'm going to shake those up like this, shake this one up like this, and I'm going to shake this one like this. I will just let them sit there and see what happens as we make observations. So try to pay attention to what you see in front of you here as I now do another experiment. This experiment is with what? What am I holding in my hand here? What does it look like? You're on the cell phone describing someone else, right? It looks like a hose, okay? How long is the hose? What color is the hose? Do I have to ask all the questions all the time, right? Yeah, we all have to get in the game. We have to be active participants. So this is there's an opening here. Yeah, I can see you at the end there. There's an opening there. So here's what I'm going to do. Can you hear the sound of my voice?
Yeah.
You can hear the sound of my voice?
Yeah.
You know how that happens?
Yeah.
My vocal cords vibrate. They push the air, create a wave that hits your eardrum, And something really fascinating happens after that. Because electrical impulses go from the eardrum to the brain. And the brain can make sense, usually can make good sense, unless it's an illusion of some sort. Right? So here's what I'm going to do now. I'm going to take this, I'm going to go like this. Did you hear that? So what was happening is that by my turning this faster and faster, air was flowing through, and this is a corrugated tube, and it succeeded in generating a sound wave. It hit the eardrums, and all kinds of fascinating things happened after that the neuroscientists now study and help us learn more about that. So in order to have a sound wave, you need a vibration. Here's a vibration. You hear that, right? You take it for granted. Here's an experiment we're going to do together that relates to sound. I would like you to have two fingers like this together. And now try to do that. Okay. Now, that's not very loud, is it? You know why it's not very loud? Because we're not compressing enough air. So now I would like you to open your hands like this. Open your hands like this. And then go like this. Now cup your hands. Thank you very much. Now, when was the sound louder? When you cupped your hands or when your hands were wide open? You're not sure? Do it again. Do it again. A sound is louder when we compress more air. And when we compress more air, as we do right now, that's louder than this. That's why when we applaud like this. We don't applaud like this, right? So, well, it depends if you like what you're applauding or not. So, all right. So sound waves are generated, and it's through the senses that we learn, and we try to make sense, as the saying goes, of what is going on. What is going on over here? Did we leave this experiment? Did we neglect this experiment? No. We just let it sit there. There's a change, you say?
Change.
Okay, what happened?
Well, it got lighter.
What got lighter? The glass got lighter? The rubber stopper got lighter? We have to train ourselves to be accurate in what we say, right? Have I made this point before? So this one is almost clear and colorless, but if I go like this, and this one, if I go like this, and even if I go like that, tell me, isn't this color pretty? Isn't it beautiful? Weren't these color changes beautiful? It's amazing how the brain constructs the information and tells us that something is beautiful. It's amazing how the brain takes sound waves and sorts them out from being beautiful music to being noise. This is why we do science, to satisfy our curiosity and to learn about a variety of properties of the world that we live in. Here's a question for you that relates to water. Does sound travel in water differently than it travels in air?
Yes.
Don't guess. It's a 50-50 guess, right? Think about it. So that's something I ask each one of you to do. T-H-I-N-K. Think. Always think. Always think. Count at least to 5 before you say something. Unless you're super excited about it and you want to give somebody a big round of applause, that'd be fine too. So think about it, and make sense of what you're about to say. But always say it so we can share and help each other in making the proper observations. So here's one. Why do you suppose the color changes when I shake it like this? And when this one, I don't have to shake it as much, but I like to shake it that much. So why do you suppose? Because we're mixing different chemicals. And do you suppose all the chemicals are in the liquid phase in the water? Is there anything above the water? What's above the water? Air. What's in air? What are the two gases in air? The two major gases. Nitrogen and oxygen. And it's about 80% nitrogen and 20% approximately oxygen. And you know what? Maybe it is mixing what's in the liquid with the air. And maybe not. Those of you near the front, can you see that there's a ring of coloration at the top of the surface? That's a hint that we, actually that's a clue. You know the difference between a hint and a clue? Uh-huh. A hint is something that someone gives you. A clue is something that you find. You know, you walk around and say, I have no clue. Well, here's a clue. You found this one. So maybe there is a reaction between what's above the surface and what's in the liquid. And maybe the dyes behave differently because they have different properties dissolved in the water. How are we doing with the bead bottles? Have they all disappeared someplace? Or they're all there, right? Right? If you would be kind enough to pass them back, 3 on each side, I would appreciate it. And I once again invite you to visit the website and to learn more about, thank you, to learn more about science and about science and the arts. In many of the presentations that we do, we have people playing musical instruments, we have people sing, we have people do all kinds of active participation in what we do. All right, so I have 3 on this side. I have 3 on that side. Thank you very much. Thank you very much. Now, I'm going to ask you to focus your attention on this large glass beaker. This beaker is empty except for air. It has a volume of 4 liters. And if you look at it right now, you just learned how big 4 liters is, and you cannot unlearn it. You may forget it. Those are 2 different things. Think about it. I'm going to take a magnet coated with Teflon and put it down there. Turn the light on and turn, there's a motor below. Now the bar is spinning. Can you see that? Or are the cylinders in your way? You can see it? I don't have to move the cylinders back? I'm happy to move the cylinders back so you can see. Now it stopped spinning, so I'm going to turn it on again. As we look down at this bar, it seems to be spinning in what we call a clockwise direction. You see that, right? Now I would like to ask you to do something that we always do in science. Try to visualize this bar spinning as we look down at it in a clockwise direction. Try to visualize looking at it from below. In other words, imagine there's a ceiling fan up there. And the ceiling fan, as we look down, is spinning like this. And then I see some of you trying to do that. Then you look up, what do you see? Clockwise or what? If down, looking down at it, it's clockwise. What happens when you look up? You're getting me confused here. Is this my right hand or my left hand? Right. That's my right hand. I look up, and it's my right hand. Now, I look down, and it's still my right hand. What's going on here? You know what's going on here? Is that you and I know the code. If you find a glove, you can instantly say whether it's right-handed or left-handed because you know the code, right? Let's try to straighten this thing out all together. I want everyone here, everyone watching, to stick your finger out like this. And I want everyone to rotate in a clockwise direction. Hey, I said clockwise. What are you doing? I'm going clockwise. Watch. I'm going to turn around, be like you, clockwise. But when I turn like this, what direction do you see me moving my finger in? So you have to think about the perspective. You have to think about your vantage point when you make observations and try to make sense out of them. Otherwise, illusions will take over, and that would be not a very good thing in the end result. And by the way, where does this notion of clockwise come from? Anybody? Clocks, yeah, I know from clocks, yeah. Where does it really come? It comes from the sundial. And as far as we know, the sundial was first used in the northern hemisphere. So here's another visualization I want you to think about. In the southern hemisphere, is the movement the same or not the same? You think about that. All of these are good thought questions for us, and they have good answers also. Don't look it up on the internet. Think about it, talk it over with other people. Look it up on the internet, but after you think about it and talk about it with other people, and make sure the information is reliable on the internet. All right, so what I'm going to do is take 3 clear and colorless liquids. I'm going to mix them together. Oh, before I do that, I'm going to do this again. I love this. This one, I have to shake it a lot harder.
Why don't you tip one upside down?
What?
When it turns clear, should you tip one upside down?
Tip it upside down?
Yeah.
You mean like this?
Yeah, and then we should see if the color changes.
Okay. Well, I tipped it upside down. Now I have to wait for this?
No.
Well, in science, we're patient. You know, if you do anything worth doing in life, you have to be patient. And you have to pay attention to it. And you have to give meaning to it, right? So this is a very good question that you ask. Maybe if I do it like this. All kinds of experiments that you can do. Try it out. All right, so I come back to this experiment. I take a clear and colorless liquid, and I put it in the beaker. It comes out, glug, glug, glug. There it is. And then I take the second clear and colorless liquid, and I add this one. Anything interesting happened so far? Well, the volume increased. That's common, right? And there's a slight change in coloration. And it looks like there is a tornado. I hope this is the closest you'll ever come to a tornado. And then I'm going to take the third liquid and add that. Anything interesting happen?
It turns yellow.
A beautiful change. I see a blue color here. What's going on? Look, the last time I looked at the liquid in the beaker, the color was blue. You're not paying attention to me anymore. Tell me when to look. Shall I look right now? No? Okay, I won't look right. Tell me when to look. The last time I looked, the color was blue. Right now? You sure? I don't want to trip over anything here. It's blue, deep blue. Maybe you can help me better on this side. Tell me when to look. So, right now. Henry, when shall I look? Right now. You sure? Yes or no? No. He said no. Okay, don't look. Right now? Absolutely sure? Every time I look at it, it's blue. Why is everybody screaming? What is it that you are doing that I was not doing? Oh, you were looking all the time? I was looking all the time. I was looking at you all the time. You were looking over here. Remember I said, pay attention. Pay attention. Most of this liquid is water. Most of it is water, okay? Water has dissolved in it a lot of different substances, including hydrogen peroxide. This has in it 30% hydrogen peroxide. In the drugstore, you can get 3% hydrogen peroxide, not this one. And then there are other chemicals in there, including malonic acid, potassium iodate, manganese sulfate, potato starch, sulfuric acid. This yellow color was the color of iodine. It combines with potato starch, gives a blue color. That comes back again. And these colors continue to oscillate. The overall reaction is the decomposition of hydrogen peroxide to water and oxygen gas. You see some bubbles in there? Those are oxygen gas bubbles. Actually, there's some carbon dioxide bubbles in there too because of the other ingredients that are in there. This is called a chemical oscillating reaction. And you're paying attention to it. And I'm paying attention to it. And you and I are noticing that the duration of the dark blue color now is getting longer and longer than before. This chemical oscillating reaction is one of about 50 known such reactions. But this one is very special to me. It's special for two reasons. One, it was discovered by two high school teachers. And it's named after them. It's called the Briggs-Rauscher reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. And in 1973, they published a paper in the Journal of Chemical Education describing this beautiful, captivating behavior that we are enjoying right now. The second reason it's special to me is that it took researchers, high-powered researchers, members of the National Academy of Sciences. It took them 9 years to figure out what's going on here. Were they patient? Yes. Were they paying attention? Yes. This is why we do science, to satisfy our curiosity and also to advance knowledge and to contribute to technology and for the betterment of society. Now that we know that there are 24 different elementary steps in this overall decomposition of hydrogen peroxide, we can control the conditions and produce the nice effect that you and I have been enjoying for several minutes right now. Once again, you notice the deep blue color is lasting longer and longer. This is the Briggs-Rauscher chemical oscillating reaction. Well, you've been a great audience here, and I really appreciate your interaction with me. Both Oliver and I want to thank you for being here. But more importantly, I want to thank my colleague, Dr. Gary Essenmacher, who is sitting right there, for traveling with me across the state the past few days and coming to Waterfest here in Sturgeon Bay. And mostly I want to thank Coggin for all the efforts that she and others in this area put toward Waterfest and toward the betterment of the use of science and technology for advancing the human condition. Thank you all very much. Thank you, thank you. I have one more experiment. It's kind of an encore, and because someone helped with us, so help me with this one. So this is a set of beads. They are all connected to each other, and they were placed in this mug. Mugs are usually used for other purposes, right?
Yes.
But this is a good use for this purpose. I'm going to take the one end of the chain of beads, and I'm going to hold this up here and then let go. This was an easy way to siphon all the beads out. And this is related to the properties of fluids, although this is not a fluid. This is a demonstration that helps us understand ways by which siphoning happens. And if I take this and put them all in here and find the end, where's the end? Is there an end here? Where? There's no end to this. Where is the end? Okay, here's, all right. And since you helped with this, can you put them back in there? Just dump them in there. Dump them all together. Yeah. All right, so thank you very much. Give her a hand for helping out. So now I'm going to do what we always do in science, repeat the experiment, right? So I take this, I put it down there, and it's not siphoning down. Why is that? Because the order in which you put the chain back in is important. She and I just dumped it in. But before that, this is how we really like to repeat the experiment. Now here's another one. You ready for this? All right? Here we go. Now you're going to put them back in. It's going to take longer to put them back in the proper sequence than it took to get them out. So this is related to the properties of all kinds of materials, including polymeric materials, and how they flow and how they interact with each other. So you can just dump them in there. So thank you again very much.